My name is Mark Warner. I'd like to talk to you about the physics of angular momentum and spin. We have a challenge, and the challenge is this. I would like to demonstrate this challenge by taking this wheel and starting to analyze it. So this is a wheel. It weighs something. It's got a weight, which is a vector, which acts down from its center of mass. And if I support it with my hands, it's in equilibrium. And then if I let my right hand go, I'm sure all of you would understand that I have a weight force down in the middle. My hand is pulling up on the side, and the wheel flops over. That's not unexpected. It's elementary. There's a turning effect from the pair of forces. So now I would like to show you what happens when I take this wheel, spin it up, do the same as I did before, and let go with my right hand. And you see that the wheel magically floats through space. The same forces are acting in the string and from the center of mass, but the wheel floats through space instead of falling down as it did before. So the purpose of this lecture is to explain this behavior, for which we need a physics and mathematical machinery, and to explain it in 4 short cameos. And these are to recall what linear motion and momentum is, and the forces involved, to look at angular motion, in particular in the case where it is conserved angular momentum, and then to look in the case where angular momentum changes by the action of an external torque, and then fourthly to conclude talking about quantum spins, which are rather unusual. So let us continue now with the first of these sections about motion. And these are the laws of motion in a straight line. They're the laws of motion from Isaac Newton. And we have motion in a straight line. If we have a mass here of mass m with a velocity v, it's a vector, don't forget, then if we have a momentum p, which is mass times velocity, then Newton's first law says that if there's no force acting, then the body continues in a state of unchanged momentum. That is, it continues in a straight line if there's no force acting. That's the simplest of the Newton laws. And then Newton's second law is that if we have a momentum p and a force acts, then that force acts to change the momentum in the direction of force. So the changes of momentum are in the direction of the force that's applied. And Newton's second law more precisely says, the way that you, I think, have often seen it, F equals ma. A is dv by dt, so it's F equals m dv by dt. But the real formulation of Newton's second law is that force equals the rate of change of momentum. And that's F is equal to dp by dt, and the directions matter. So let's look at a simple case first, and the simple case is of a ball being bounced off the floor. So the ball comes down with a speed v. It has an impulse from the floor at the collision, which causes it to change direction, and if we think of it changing elastically, then we find after the collision the ball is traveling up with a momentum minus p. The magnitude of the momentum change is 2p. So we had p going down and then p going up, and the change is 2p, and that change is caused by the action of the force, and the force times the time is the change of momentum. It's called the impulse, and you dealt with that, I think, earlier with Mr. Hughes. And now we come to a case in linear motion, actually in a circle, that will be very useful when we deal with angular momentum. And that's the case where we have a particle going around in a circle, and in that case, the momentum changes from its blue value there to the green value in a little instant of time, and the change of momentum is inwards. So here we see a triangle of momenta. And that triangle shows you that the change from blue to green is an inward momentum, and that momentum is in the direction of the force which is inducing the circular motion. And that force is a very real force, and I'd like to demonstrate that to you with a piece of simple apparatus. And it is this. We have a handle, and through the handle passes this string, and the string is what provides the force to the ball to keep it in circular motion. So you see the ball is going around rather fast, and the weight acting down is actually redirected through the handle and is the inward force causing this acceleration. And this acceleration is towards the center of the motion, and it doesn't change the energy, it just changes the direction of the force. If you ever had any doubts as to whether that's a real force, then you can see how great the force was from the masses that provided it.